begin the read of Chapter 12, Erosion and Weathering, and this begins the Section 1 read. Weathering. Granite forms deep underground where pressures and temperatures are high and water and oxygen are lacking. When granite is pushed up to Earth's surface, pressures and temperatures decrease dramatically. Granite is exposed to water and oxygen. As a result of these changes, the granite begins to weather. Weathering is the breakup of rock due to exposure to processes that occur at Earth's surface. Geologists group weathering processes under two headings: mechanical weathering and chemical weathering. Mechanical weathering, or disintegration, takes place when rock is split or broken into smaller pieces of the same material without changing its composition. Mechanical weathering is also called physical weathering. Chemical weathering, or decomposition, takes place when the rock's minerals are changed into different substances. Although mechanical and chemical weathering are often studied separately, they almost always act together. Mechanical weathering. Mechanical weathering processes include frost wedging, wetting and drying, abrasion by rock materials, plant and animal activity, and exfoliation that occurs as a result of upward expansion. Ice and water. Water occupies about 10% more space when it freezes. This expansion puts great pressure on the walls of a container. Consider a pail of water left outdoors in freezing weather. The pail may split open when the water freezes. In the same way, water held in the cracks of a rock wedges the rock apart when it freezes. This process is called frost wedging or ice wedging, and is common in places where the temperatures varies from below the freezing point of water, 0 degrees Celsius, to above the freezing point. It occurs mostly in porous rocks and in rocks with many cracks. In Picture 1, rainwater enters existing cracks in a rock. In Picture 2, the water expands as it freezes, wedging the rocks apart. Frost wedging also occurs in places where there are frequent freezes and thaws. Bare mountaintops are especially susceptible to frost wedging. The vast fields of large, sharp-cornered boulders that are often found on mountaintops are pieces of the mountain that have been broken off by frost wedging. Frost wedging also causes potholes to form on paved streets and highways. Here the process is helped by ice heaving, which happens when water in the ground freezes and lifts the pavement above it. When the ice thaws, the pavement collapses, leaving a pothole. In addition, liquid water plays a role in mechanical weathering. Repeated wetting and drying can break up shale and other rocks that contain clay. These clays, which absorb water easily, swell up when they are wet and shrink when they are dry. Repeated swelling and shrinking cause the rocks to break apart. Abrasion. Water, wind, and ice are capable of moving rocks. Water can tumble sand, pebbles, and even boulders along stream beds. Wind can blow sand and small pebbles across a rocky plain. Glaciers, which are moving masses of ice, carry rocks over great distances. Even gravity moves rocks. As moving sand, pebbles, and larger rocks grind and scrape against one another, these rock materials are worn away. This type of mechanical weathering is called abrasion. The sand that you walk on at the beach is a product of abrasion. Rocks and pebbles get ground down into fine particles of sand as they are carried by rivers, streams, and ocean waves. Plants and animals. The growth of plants and the activities of animals contribute to the mechanical weathering of rock. When mosses and other small plants grow on rocks, they wedge their tiny roots into pores and crevices. As the roots grow, the rock splits. Larger shrubs and trees may grow through cracks in boulders, causing the cracks to widen. Ants, earthworms, rabbits, woodchucks, and other animals dig holes in the soil. These holes allow air and water to reach the bedrock and weather it. Burrowing animals also bring rock fragments to the surface, where the fragments weather more rapidly. Upward erosion. The upward erosion of rocks that are formed deep underground may result in a mechanical weathering process called exfoliation. For example, granite becomes exposed when it is lifted up and the rocks above it are worn away. The removal of these overlying rocks reduces the pressure along the surface of the granite. Upward expansion causes the granite to break along curved joints that are parallel to the surface. Such joints can be exposed in peaks or outcrops. Over time, large sheets of loosened rock break away from an exposed outcrop, as shown in the diagram below. Exfoliation forms rounded mountain peaks called exfoliation domes. Spectacular exfoliation domes occur in Yosemite National Park, California. Other exfoliation domes include Stone Mountain in Georgia and Sugarloaf Mountain near Rio de Janeiro, Brazil. In the graphic of upward expansion, granite and overlying rocks are uplifted. Eventually, the overlying rocks are worn away. As pressure from the overlying rocks is relieved, the granite expands and cracks along curved joints. Sheets of loosened granite break away. Chemical weathering. Chemical weathering occurs almost everywhere because water or water vapor is found almost everywhere. All chemical weathering involves water or water vapor. Other agents of weathering include acids and oxygen. Water and chemical weathering. The chemical weathering by reaction of water with other substances is called hydrolysis. Common minerals that undergo hydrolysis include feldspar, hornblende, and augite. When these minerals are exposed to water, they dissolve into ions. These ions slowly react with the water and form clay minerals such as kaolinite. Water's chemical effect on minerals is increased by the presence of acids that are dissolved in the water. A common acid found in water is carbonic acid. This weak acid is formed when carbon dioxide, one of the gases present in Earth's atmosphere, dissolves in rainwater, falling through the air. When rainwater containing carbonic acid seeps into the ground, it reacts chemically with many common minerals, including feldspar, hornblende, augite, and biotite mica. Elements such as potassium, sodium, magnesium, and calcium are dissolved, and the original minerals are turned into clay minerals. Carbonic acid has an even greater effect on calcite. When carbonic acid reacts with calcite, the calcite dissolves completely. Unless the calcite is impure, no clay minerals remain after the reaction. The dissolving action of carbonic acid has hollowed out great underground caverns in limestone bedrock. You'll learn more about caverns in Chapter 14. Sulfur dioxide, nitrogen compounds, and carbon dioxide released by industries react with water in the atmosphere to form acid rain. Acid rain is rainwater that contains unusually high amounts of acids that can be traced to these pollutants. In addition to the damage that acid rain inflicts on the environment, acid rain also increases the rate of chemical weathering. Acid rain can cause structures made of concrete, stone, and metal to wear out more quickly. Acids that are formed by the decay of dead plants and animals are dissolved by rainwater and carried through the ground to the bedrock. These acids react with minerals and contribute to chemical weathering. Oxygen and chemical weathering. The brown or red color of some exposed rocks may be the result of a process called oxidation. Oxidation, which is the chemical reaction of oxygen with other substances, is very effective at weathering minerals that have iron in their chemical formulas. These minerals include magnetite, pyrite, and the dark-colored ferromagnesian silicates, hornblende, augite, and biotite. Oxidation of these minerals results in a formation of different types of rust or iron oxides. Sometimes the rust that forms is a red iron oxide called hematite. Sometimes a yellowish-brown rust called limonite is formed. Rates of weathering. Under average conditions, weathering is a slow process. Several factors affect the rate of weathering, including the amount of a rock's surface area that is exposed to weathering influences. The composition of rocks and climate also affect rates of weathering. Surface exposure. The rate at which a rock weathers is affected by the amount of the rock's surface that is exposed to chemical weathering processes. As shown below, when a rock is broken into smaller pieces by mechanical weathering, more of its surfaces are exposed. Thus, breaking a rock into smaller pieces causes the rock to weather more quickly. In this graphic of surface exposure and weathering, mechanical weathering breaks a large rock into smaller pieces. More rock surfaces are exposed to weathering, contributing to the breakdown of the rock. Composition of rock. Depending on their composition, various rocks respond differently to the same weathering processes. The rock layers in a photograph at the left have different compositions. So even though the rock layers have been exposed to the same weathering processes, the layers have weathered at different rates. In some places, remnants of rock that are more resistant to weathering have protected the layers of less resistant rock beneath. The taller formation in a photograph has a cap of more resistant rock. The rate at which a given rock weathers also depends on the type of weathering to which it is exposed. Because quartz does not react much with water, oxygen, or acids, it is almost unchanged by chemical weathering. Because quartz is hard and does not have cleavage, it also resists mechanical weathering. Gradually, however, quartz is broken down into smaller particles. In contrast, feldspar, hornblende, biotite mica, augite, calcite, and gypsum are affected by both mechanical and chemical weathering. Mechanical weathering breaks these minerals into smaller fragments. Chemical weathering turns these fragments into clay minerals. Some minerals, such as calcite, gypsum, and halite are also dissolved and carried off in solution. Sandstones, quartzites, and quartz pebble conglomerates are only as durable as the cements that hold them together. When the cement gives out, these rocks fall apart into the grains that compose them. Rocks that are cemented with calcite are subject to more rapid weathering. Rocks cemented with silica are more resistant to weathering. Quartzites and silica-cemented sandstones and conglomerates are among the most durable of all sedimentary rocks. Shales are the most easily weathered of the sedimentary rocks. They split easily between layers and in time crumble into the clay minerals from which they were formed. Marbles and limestones are fairly resistant to mechanical weathering. However, the calcite that constitutes marble and limestone undergoes slow attack by acids and water. In moist climates where rainwater contains dissolved acid, rocks made of calcite are less durable than quartzites or sandstones. In dry climates, there is little dissolved acid, and limestones are among the most durable rocks. Climate. Climate is another factor that affects weathering processes. In general, warm, wet climates are conducive to both chemical and mechanical weathering processes. For example, most igneous rocks and many metamorphic rocks weather rapidly in wet climates. When these rocks are exposed at the surface, they often become cracked because of differences in temperature and pressure. Mechanical weathering widens the cracks in the rocks, exposing minerals to chemical weathering processes. In regions with cold or dry climates, mechanical weathering plays a greater role than chemical weathering in breaking down rocks. For example, wind-blown rock materials can wear away rock surfaces in dry desert climate. At this time, you need to answer questions 1 through 8. You can use the back of that notes sheet I handed out, and I will collect them at the end of class.